Hello. Um, Now, first thing I want to talk about today is the title. Why did I choose physics of mind rather than the familiar cognitive science? Well, there are two reasons, basically. First of all, physicists go about their work a bit differently from cognitive scientists. The example is physicists would like to talk about dynamical systems, whereas cognitive scientists might prefer computer models. And the second thing is that this talk will actually connect physics and mind, so therefore I'm calling it Physics of Mind. Now, before I go on, I'd just like to credit the people I've been working with on this project. 𝐭𝐫𝐢𝐚𝐝 is an expert in coordination dynamics, and 𝐼𝐶 introduced the circular theory idea that I'll be discussing later. And my main collaborator is 𝐭𝐫𝐢𝐚𝐝, and I'll just mention a little about him at this stage. We've been interacting via Zoom, and that's made it a bit difficult to work on a paper jointly, though we've just been discussing ideas. So we've been posting preprints separately, and here are two of his preprints. You can see something about them from the title: unified something field, how self-selected fluctuations can underlie reality, and diversity from a fundamental unity and its projections. He's interested in specifics like how we can connect mind topics with the standard model, and also general issues like the role of modeling and the code theoretic and matter aspects of reality. Now, why is this topic of particular interest to me? Well, I've for a long time been involved with the fact that physics doesn't adequately deal with activity of mind. And in fact, I believe that mental activity is primary, and physical laws derive from this. This is an idea which John Archibald Wheeler was proposing, the observers having a role in determining the laws of nature. And our ideas are somewhat similar, but we go beyond Wheeler's in certain ways, as I'll be explaining. Now, over years, I've been studying quite a number of approaches to the mind, and what's interesting is that there's overlap between these different theories. They appear to be producing, coming up with identical pictures, and what I'm now doing is putting these different ideas together, because people specialize and they're not aware of what people in other areas are doing. And when you put them together, very interesting things can come out. Well, two of these things are, there's actually two books, Ekblad's Scheme Theory about schemes, Winograd's Understanding Natural Language, which is a computer model of language. And besides this, the idea of coordination comes in. Now, what links the two is the concept of flowcharts, and we'll see that when I get into details. I'll just show you a flowchart. This is about what happens if a lamp doesn't work. You do various things. You first make sure it's plugged in. If it's not, you plug it in, that fixes it. If not, you check the bulb and so on. So flowcharts also have a role, of course, in computer science, and they give you a picture of what a program is doing, and they are great help in designing programs. What Ekblad has done in her scheme theory. Now, Ekblad actually talks of a hierarchy of schemes, and here's an example from a book. Now this blue rectangle is showing you one level. It's actually two levels in one, and that is enclosed in a higher level, the red rectangle. And hierarchies are another thing which is common to very many approaches, like coordination dynamics, for example. Okay. Now, in a book, 𝐼𝐞𝐚𝐿 talks of the static and dynamical aspects of the scheme theory. So that hierarchy is the statical aspect, and dynamical aspect would talk about things that cause the structures to change. And one thing she does is to bring in concepts due to Piaget. Piaget talks about circular reactions, and so a way to picture this is if a scheme gets stuck, then you may keep trying a way of dealing with it till it becomes unstuck. So there's some circular processes built in, as it were. So that's an important part of the picture. Okay, I eventually want to get to how all this explains language, so let's move on. I'm going to be talking about Winograd's computer simulation, and he talks about systemic grammar. And systemic grammar is an idea which is different from Chomsky's, whereas Chomsky just talks about the structure of the language, the syntax. Systemic grammar asks what do these structures do, so that's really a very different and a picture more connected with reality. And so Winograd brought that into his program. He made lots of simulations of the functions of various pieces of grammar. And anyway, I want to talk about flowcharts, and here's a flowchart for one of these particular things. This is how his program, when presented with a verb group, decides what tense it is, something pretty complicated. But the thing is, it all works. And I'll give an example of it working. What he did was to program a simulated blocks world, and then he could ask questions about it and ask the program what to do, or ask it to do certain things, like here we have, will you please stack up both red blocks and either green. I can't see it as it's behind my picture, but anyway, it's a fairly complicated sentence, and it because he put in all these functional bits, it all worked out. It did what it was asked. It could understand language. Okay, now I want to show how this systemic grammar concept, it can explain how language works so effectively. I'm going to give an example, responding to a request, something we've seen in the Winograd program. So the idea is simply that there is a specialized system for dealing with this common aspect of language. Responding to a request is one of the ways language is used. So the idea is that as language evolved, people found a specific technique for dealing with, for using language. So gradually this particular system got consolidated and integrated into the rest of the language. So it's really a very simple idea. It's connected with how schemes evolve. It's a means-end situation. Certain ends can be achieved by particular means, and so the systemic structures evolve. And this is something that involves a joint system, two individual systems coordinating in the way prescribed by the flowchart. And this coordination is something familiar in computer science, actually, because computing systems often require coordination with other systems. For example, the World Wide Web, that depends on all sorts of systems working together. For example, web browsers and web clients. There's the World Wide Web protocol, which says exactly how the arrangement should work. Now, here I'd just like to say something for the experts. What is a flowchart from a physicist's point of view? Well, you could say it's an abstraction, but what it actually consists of is a kind of map. I guess a map is an abstraction. The underground map is an abstraction of real life. Similarly, a flowchart is a map, but not in real space. It's in state space. And also the abstractions are at many levels, which is something that accords with coordination dynamics, which I will be coming to next. So let me now outline what coordination dynamics is. I'm going to take the definition from a review article by a book chapter by 𝐭𝐫𝐢𝐚𝐝, which you can find on ResearchGate. Saying coordination dynamics describes, explains, and predicts how patterns of coordination form, adapt, and persist and change in living systems. Now, that is an experimental field. You look at behavior, but also you create models to try and explain that. One part of the picture is synergies, which are just like with schemes, there's a hierarchy of synergies. Now again, I'll take Kelso's definition. Functional groupings of structural elements temporally constrained to act as a single coherent unit. Now, temporally constrained is an important thing because groups form and dissolve, and new groups form instead. They group in different ways, and this is one of the things in the model. There's something called the 𝐻𝐾V model. And that accounts for versions of stability. Some things are certain parameters, have a system which is very stable. You have control variables which can change things. Some versions the system is stable when you change the control variables, or it may cause you to hop from one configuration to another. All sorts of things like that. I'll also mention a thing of interest in physics, in that phase relationships play an important role here, because systems can lock in phase or they can become independent, so that's a part of it whole. And the way groups form is probably related to having a lot of systems coming together with fixed phase relationships. Now, the next thing I want to discuss is semiotics. This is really pretty ancient. It was introduced by Peirce in the 19th century, I believe, and is extremely complicated. Peirce spent most of his life developing the ideas. But basically it's about signs and their meaning. And one key point is it involves triads, groups of three, and in one context, a triad is a sign of some kind, what it refers to, and also context that determines the significance of a sign. An illustration is a red traffic light. That means stop, but only in the context that you're driving a car. Light could be used to mean something different, like there's an emergency. Okay, so it's connected with final causation because you do something for a purpose. This, by the way, is something that there was in scheme theory. Those diagrams had an I and F, the beginning of a bit of scheme and the end, the beginning of a bit of flowchart and the end. Another aspect of it. So it involves triads, and so there's more complicated kind of correlations. So the mathematics would be different. Another interesting thing is that signs are classed into three things, or at least their mode of action is three types: iconic, indexical, and symbolic. Iconic is a sign that's closely related to what it's about. Indexing is a sort of way of referring, it's a way of making complex things, complexes of signs, work. The interesting thing is a symbolic type of sign, which Terence Deacon has talked about in some of his work. The difference between symbolic signs and the other kind of signs is that they can work with things that are not present. Indexing means there's something in the current situation that you're going to index to be able to work with it. Symbolic signs are not subject to that constraint, so they're really very abstract. Okay, I'm going to leave semiotics there. It's another kind of picture with its own details. So now I'll come on to modelling. This is something Robert Rosen, who wrote a book, Life Itself, which a esoteric account of what biology is, where he said we have to do it completely different to the way science usually works. It involves relations, so there's relational biology. Now, his modelling is connected with organisation. Two systems are related to each other, and one in some way represents the other. But they can link together in such a way that one system organises the other. So it's the abstraction of organisation comes in here. And you can relate this to survival. The idea is that a badly organised system will tend to disintegrate and dissipate. If it's well organised, then you'll have a stable situation, and more stable situations are more likely to persist. That explains why we have organisation that works. Very simple. It's happened with language that people find how they can use language in such a way that you can answer questions or obey commands. That is associated with an organisation, flowchart, etc., etc. So that's a nice thing which fits in with everything else. Well, now I'd like to talk about Alexa Yardley's very unusual circular theory. Here's a picture from a website which is sort of illustrates what's happening. What have we got here? Well, we've got pairs of objects here, combining into one and splitting into two. So on the one hand, it's about relationships between single objects and pairs, and that can occur in various contexts. One, I would guess, is that there can be a phase transition where a single object splits up into two, and so on. There can also have a triadic element with this single object affecting relationships between two others. Also, you can have two things here becoming two different things. And here there's a point that this is like the diameter of a circle. Well, I'll go into that in a moment in the next slide. Now here are the various ways one can interpret that diagram. I've already mentioned two entities might act as one and reverse. One might think of it as a critical point or a bifurcation. A bifurcation is a mathematical concept where one entity splits into two, or it might be a phase change. She talks of systems giving rise to systems of systems, and then systems of systems of systems. In other words, you might have a system which, as conditions change, becomes a more complicated system of systems, and this could get more and more complicated, a bit like turbulence. Or conversely, one system might find another system to interact with, making a unit so systems can join together. There may be one total system, perhaps. Slightly different interpretation is if we don't think of one going into two, we think of one interacting with two. That's like the triadic system we're familiar with. She calls it pi, linking a line and circle. Also, she talks about pi, which is in the background and too complicated really to deal with directly. Ensure stability in a situation that is in itself markedly unstable. Well, that is something that we've had before in connection with organisation. A good organisation can ensure stability. So we can think of this as something might happen when organisation emerges, as I've already said. So in the background is something that organises the thing that's visible. Now, line being a diameter of circle is something she talks about. Now I'm going to try and illustrate this. A bit difficult as it's not a mirror image. Okay, here I have my two fingers of two entities, and now that's a line, and I can rotate, and that becomes a circle. So what have we here? We have a pair of systems which might get modified and go round in a circle. This could mean that a phase transition making two objects would be something where there's just one degree of freedom. That kind of thing is possible. Say superconducting state. Anyway, one can certainly have situations like that in physics. So that's in such a situation we have one degree of freedom. That's got a geometric aspect, the direction in a plane, and an algebraic one, a phase. So some more ideas are associated with that. So it's very interesting that if that represents a physical situation, then this might account for a lot of things. Now, the book, she doesn't do much explaining. You have to sort of contemplate deeply. And if you look at this business of define, explains, controls, these are all different things which words can do. If you say something, you can use it to define something, or to explain something, or to control something. So again, there are more details in this picture. So this is this might really be an important idea if one were to explore it in more detail. Okay, this is now, as it were, the end of part one, because part one is about this physics of the mind, new branch of physics. So in other words, mind in this sort of way is like new branch of physics, like nuclear physics, solid state physics, the physics of the mind. And I think putting all of these ideas together, we understand quite a bit of the complexities. So progress should be possible if people become aware of this, how it all fits together. It will also appear, and this will become clear in a moment, that this new physics would underlie the physics we have at present in just the same way that atoms and molecules are the underlying basis of macroscopic phenomena. So I want to show how this mental substrate can give rise to the physics that we know about. That'll be part two of the lecture. In other words, mental processes are the actual source of physics. This may be expected to have dramatic consequences for our understanding of nature. So let me go into that now. So how can mind give rise to physical law exactly? Well, this isn't a new idea. John Wheeler had an idea like that, based on the fact that, according to some interpretations of quantum mechanics, observers do actually do things. In a quote from an article by 𝐸𝐞𝐚𝐝, Wheeler defined a participatory universe that requires human beings or other forms of intelligence, note, as an essential and integral part in order to enable its evolution. Okay, so Wheeler seems to have considered that you get a universe, life appeared, then life could change the universe somehow. But he seemed to want life to work backwards, and that doesn't seem a very good idea. However, one can get around it by just supposing that this intelligence worked initially before the universe existed, and created the universe, and also did things once the universe had been created. All by these kinds of mechanisms. Now this is interesting that it in a way integrates science and religion, a further integration, because of course in religion so there's some entity that creates, that works on the universe, some say on what it is. Some people may not like this, and yet we seem to be forced to this view from our position. Okay, so this also helps to solve the origin of life problem, because the origin of life problem is how on earth do we get from chemistry to the kind of life we're familiar with? And of course, if there's an intelligence around that knows how to do it, then that makes it less of a problem. And furthermore, it could be, as the intelligent design people say, that a part of this process would be to create man in the image of the creator or whatever. But anyway, this all could come out of quite reasonably from this rational picture that I've been explaining. Well, now I want to amplify this idea by saying what is involved is really technology, and this shows the interesting way in which this might happen. The first step is that mind can produce mathematics. Mathematics is just a particular language, but it happens to be a language which is, besides interesting in itself, is also the source of technology. What happens is that you can create now mathematical systems, and mathematical systems you can then reason with them and prove theorems. So mathematics is a productive thing for mind to do. But now mathematics can be used for technology, and here, as you see in this diagram, mathematics is giving rise to technology, and mind is part of this process. So it first creates mathematics, then it uses it. Now, the next thing is that I talked about devices. Well, this is an interesting aspect of what's going on, because the technology is something that involves various devices. Okay, now let me say something about devices. First of all, I'd like to define a device. Something that enables something to be done that could not be done without it. Now, the interesting thing is that there are mathematical as well as physical devices, if you go by this definition. For example, real numbers are a device that enables 2 to have a square root. 2 does not have a root if you confine yourself to rational numbers, but when you change your system to real numbers, then suddenly 2 has a square root. Similarly, if you go to complex numbers, -1 can have a square root, and you have a complex plane instead of a real line, and the complex plane, very interesting properties such as analytic continuation. If a function can be differentiated, then you can move on from one place to another. Now, I was recently having another look at Penrose's Road to Reality, having got myself a Kindle version, which was much more manageable than this enormously heavy physical book. There's another enabling device, the Kindle. Okay, well, this very lengthy road that Penrose talks about takes you eventually to current physics, things like string theory. And string theory involves pretty elaborate mathematics, and Penrose takes you step by step through the development of this mathematics, which you can think of as a collection of devices of this kind. So let's relate this now to the picture of how I envisage mind creating reality. You say that these entities that did the structuring of reality, they were trying to develop, their aim was to come up with some useful system, say a universe, which would contain the kind of things they wanted to contain for some reason or other. So they had to figure out how to do it, and what they did was to develop mathematics, various kinds of systems, till they eventually came up with a system like ours. So, that would be their advanced technology, as I considered technology a little while back. Okay, some examples. One thing is a manifold, which is a generalization of a space. And Penrose argues that you can make a manifold by putting things together. You keep putting things together till you get something bigger and bigger, and you join it up in a certain way, and that's your manifold. So they could create the shape of the universe they wanted. Then symmetry may involve transformations that are useful, so you can go from one kind of system to another. Groups are mathematical entities that allow you to combine operations and so on. So I think this is an interesting picture, which actually my collaborator has a sort of picture like this. He's trying to get to it. So you may therefore end up with a new physics, which is not just how mind works. It's also about how mind worked to create the kind of universe we got, including perhaps content such as man, coming from the idea of man, as Ardley suggests. And so I personally think that the people who deny intelligent design are the irrational people. Intelligent design is a perfectly rational analysis to see whether the evolution could occur without design. They do not deny evolution, they merely say that it is assisted in some way. So there we are, that's all I have to say. So it's goodbye from me and the cat that sat on the map.